Now let's look at some real-world problems. A farmer has 600 meters of fencing to fence in 3 identical adjacent rectangular pastures. A long stone wall is used for one side of each rectangle. Find the maximum overall areas if each rectangle must be at least 40 meters wide and at least 80 meters long. So we're trying to maximize area. Let's think about a sketch of the situation. So we've got a stone wall. And we're having 3 identical adjacent pastures. I'm just, this is a small sketch. Adjacent. Now the length would be these, right? And each rectangle has its own width, and I'll put that here. Width, length, length, length. So the area of all 3, well, that'd be 3 times length times width. But let's think about how we can write this in one variable. So if we think about the width, if we take all 3 widths plus all 4 lengths, that's supposed to be 600 meters, right? Okay. Let's solve for W. Solve for L. 600 divided by 4, that'd be 150 minus 3/4 the width. So now I've got an expression for the length in terms of the width, so that I can write that the area in terms of width would be the width times 150 minus 3/4 the width. It's going to be a lot easier to work with if we put it in standard form. Now we also have some stipulations there. The rectangle must be at least 40 meters wide. And the length has to be at least 80. So this has to be at least 80. At least greater than or equal to 80. That'd be 280 over 3. Do the endpoints make sense? Could we have a width of 40? Well, we want at least that. And could we have a width of 280 divided by 3, which is like 90 something? It could work. Now, what other points do we need to check? Well, we need to check when the derivative is 0. So let's look at that first derivative. That'd be 150 minus 3/2 W. And we want to know when that equals 0. Multiply both sides by 2/3. And we get 2/3 of 150. It's 50 times 2, that's 100. So we have our points to check at x and at f of x. We have 40 and 280 over 3, which are my endpoints. And then we also have 100 to check. And that's a critical value. So what happens if I plug those back in to my original function? Well, if I plug in 40, and I'm just going to do it from the screen, 40 times 150 minus 3/4 times 40, I get 4,800. And then what about 100? Three-fourths. Whoops. Now the problem comes into what was our maximum value for our width? Was 280 divided by 3, which is 93 feet. So that 100 is actually out of this range. So the maximum we can make with those limitations is 7,466. An open rectangular box with a square base is made from 48 square feet of material. So a sketch of that, we've got an open box. And it said it was a square base, so this side and this side are the same, right? Now let's think about what that would be unfolded. We've got these squares cut out, right? And those are the same as that height, right? Each of these little squares cut out would be height by height, right? Height by height. Height by height. Height by height. So if we looked at it as a big picture, the area, if those little corners weren't cut out, would be x plus 2h's squared. But we're subtracting out 4 of those h's. And we want that square footage to be 48 square feet of material. Now we're supposed to only have one variable in our volume formula, which, our volume would be x times x, which times the height. But we need it to only have one variable. So let's see, x plus 2h squared would be x squared plus 2 times x times 2h, which would be 4hx, plus 2h squared would be 4h squared minus 4h squared equals 48. Oh, that's cool. X squared plus 4hx equals 48. Which variable would be easiest to isolate so that we can get our function only in one variable? Well, h would actually be the easiest. So now I have an expression for h, which I can plug back into here. Now, we could leave it like that, but that's just crazy. Sorry. X goes into x squared, gives me an x. So I have 48x minus x cubed divided by 4. 12x minus 1/4 x cubed. Do the endpoints make sense? Well, one of the endpoints would be 0. Does that make sense? Not really. The other endpoint would actually be the other place where the volume is 0, which doesn't make much sense at all. No, those would not give me a maximum volume. So the only place I really need to check is when the derivative is 0. So 12 minus 3/4 x squared, we want to know when that equals 0. Or when 12 equals 3/4 x squared, multiplied by 4/3, so when x is 4. Now what is the maximum volume? Well, first we need to make sure that 4 is a maximum. How can I check that? Oh, I could check the second derivative. That'd be negative 3/2 x. Oh, it's going to be negative when I plug in 4. So the second derivative at 4 is less than 0, which means we're concave down, which means 4 definitely will give us our maximum volume. So I just need to go find out what that is. 12 times 4 minus 1/4, 4 cubed. 4 cubed is 64. 64 divided by 4 is 16, so 48 minus 16 is 32. So the maximum volume is 32 cubic feet. Now, if we go back to that design of the trough, and I don't know which one you picked, the most widely used design is actually the trapezoidal prism. So we assume that it's created by bending up 1/3 of the sheet on each side through some kind of angle. Now we need to know what angle would maximize the volume of rainwater.